In the beginning was the Big Bang. We are told that 13 to 20 billion years ago, everything that makes up the universe as we know it was spontaneously created out of nothing through an unimaginably violent explosion. But did it really happen as we are told? A growing number of astronomers doubt it and are showing why. This is their story, the story of the universe.
The observational aspects of trying to understand the universe, I think it's reasonable to start about 100 years ago. And about 100 years ago, almost everybody in astronomy, without question, assumed that the whole of the universe was what you could see in the Milky Way. Nobody felt that the universe was any bigger than the stars that you see in the sky, associated with our own local Milky Way. And that was the situation certainly around 1905, times like that. There are well-known people who propounded these ideas. 10 years later, Einstein first proposed his general theory of relativity. Now, when Einstein proposed this, it's a theory of gravity, which means that it's a theory which should represent the whole of the universe, because it's gravitational forces that are controlling the universe. Well, Einstein made this theory around 1915, and he immediately wanted to try and use this theory to explain the universe as it then was, the so-called Milky Way system. But of course, the idea of this was that it was a static system. That is, it wasn't contracting or expanding, it was a static system. And Einstein found that his equations did not allow for a static universe unless he inserted a certain constant in the mathematics, which became known as the cosmological constant. But what happened in the early 1920s was that a very clever Russian called Friedman in 1922 found solutions to Einstein's equations which allow the universe to either expand or contract. Now that was done in the Soviet Union soon after the revolution, and nobody in the West knew about this, I think. But in 1927, a Belgian priest, the Abbé Lemaitre, as he later became, also discovered these solutions. And he went to England, and his work was publicized in Cambridge and elsewhere, and the famous English astronomer Sir Arthur Eddington and others got to know about this, and they immediately began to say, how can this apply to the current universe? Well, in the same period, in 1929, Hubble made what I still believe was the most important discovery in extragalactic astronomy in the last century, or the last century but one. He showed that if you look at the spiral nebulae, the faint spiral nebulae, the shifts in their spectra are proportional to their apparent brightnesses. And this led very soon to the idea that this fitted very well with the expanding universe, and that indeed this is the kind of universe we lived in, that what we were looking at are galaxies, Milky Ways, further and further away from us, and the further away from us, the larger the redshifts, and if that's interpreted in the way that most people would interpret it, this means that they are moving away faster and faster. So this was the original idea. By the 1930s, the front page of the New York Times said we live in an expanding universe.
When Hubble made his great discovery, it was for galaxies like our own Milky Way galaxy, and they all followed the same rule. that the fainter they are, the larger their redshift. In other words, the faster they are moving away from us. This is known as the Hubble law and directly led to the expanding universe theories. But in the 1960s, there was a new discovery, the quasi-stellar objects, often referred to as quasars. They appear as star-like points on the sky, frequently blue in color, and they have very, very large redshifts, implying that they are at huge distances from the Earth, at the very boundaries of the observable universe. Some astronomers soon found that a vast number of these strange new objects populated the regions around spiral galaxies, and were not only observable with radio telescopes, but were optical and X-ray sources as well. There were two properties of the quasars that were difficult for astronomers to understand using the expanding universe theory. The first was that if one plotted their apparent brightness against their redshifts, as one does for galaxies, one gets an unexpected scatter on the diagram, instead of the smooth curve made by the same plot done for galaxies. This seems to indicate that the quasars do not follow the Hubble law as do most other objects, and that there is no direct indication that they are actually at their proposed redshift distances. In fact, it is argued that if Hubble had first been given the plots for quasars, he and other astronomers would never have concluded that the universe was expanding. The second property was that quasars are very small, compact objects, sometimes only a light year across. So if quasars are really at their extreme redshift distances, they must then be the brightest and most energetic objects known to astronomers. So energetic, in fact, that untestable, almost metaphysical mechanisms must be applied to explain the phenomena. On the other hand, when placed at their observed distances, that is, in the neighborhood of nearby galaxies, their brightness and energies become normal, and no special mechanisms need to be evoked. This problem has led many astronomers to abandon the idea that all redshifts are due to their speed of recession away from the Earth. And if this is true, then there is no need for an expanding universe, and the Big Bang never happened. The questions arise. Is there a connection between certain types of galaxies and the quasar? Are quasars ejected from galaxies, and in fact proto-galaxies themselves? Is there some other astrophysical process which can explain the redshift discrepancies? One of the world's most controversial experts on the structure and morphology of quasars, Halton C. Arp, has for 35 years proposed just such an idea. For the heresy of opposing orthodox interpretations of the redshift problem, Arp has had to pay a heavy price, the same price paid by many a scientist with new and innovative ideas. Dr. Arp was forced to resign from his permanent position at the Carnegie Institute of Washington Observatories after the Caltech head of the Telescope Allocation Committee threatened him by saying, unless he changed his line of research, they would take away his telescope time. Due to this fact and his ongoing struggle against the established paradigms, Arp is often referred to as the modern Galileo.
I remember when I sent the paper into the first paper into Astrophysical Journal on the nature of companion galaxies, and I had a lot of them on the ends of spiral arms, so I was sure that they were connected, and I showed that they were systematically redshifted. I sent that in with naive, great expectations that people would be terribly interested and impressed on this. And the editor of the Astrophysical Journal at that time was Subrahmanyan Chandrasekhar, who had a fantastic reputation as a master theoretician and also quite an incomprehensible theoretician, and a tremendously powerful figure in the field, and editor of the Astrophysical Journal, which was probably the most powerful position in the field. And he chose not to, in his wisdom and judicial fairness, chose not to send it to a referee, but he just wrote across the paper, "This exceeds my imagination," and he sent it back to the director of my institute, Horace Babcock, with the obvious implication, you've got to do something about this staff member of yours who's doing these very bad things. And so Horace called me down to the office one day after this, and I walked in his office, into the director's office, and I saw this paper lying in front of him with Chandrasekhar's scroll across it. And Horace looked at me and said, "Well," he said, "this is just too much, and you're going to have to start looking for another job." And so all I could say to him was, "Well, if you send me that in writing, please send me in writing." And I was waiting in great trepidation for weeks and months to get something in writing, and I finally never did, so I realized that he decided to give me another chance, so to speak. So that was fairly early in the game, and then some years went by, and there was the competition for time, particularly on the 200-inch telescope, was getting more and more heated, and people were saying, "Well, we can't continue to give time to this obviously incorrect and embarrassing research that ARP does." So finally they sent a letter to me from the allocation committee, including a number of the younger members of my institute, saying that unless I changed my line of research, that they would have to take away my telescope time. At that point I considered the situation very carefully, and I figured that the evidence, although a lot more evidence could be gathered and has since been gathered since then, the important thing was not the evidence, because if it was true, it would come out someday. The important thing was the principle of scientific investigation, whether scientists could follow new lines of investigation and follow up on evidence which apparently contradicted the current theorems and the current paradigms. And I also felt that regardless of what happened to me personally, that this was the important issue, and that I had no choice but to resign on the point of this issue, so that if it developed, which I thought it would, that my line of investigation was correct, that people then in the future would say, okay, this was the wrong thing to do, and in the future we're going to have to see that this kind of thing doesn't happen again.
The observers come in now with the belief that we live in a Big Bang universe, and therefore all of their ways of understanding things are tailored to that. And they don't come in with the possibility that our alternative, or any other for that matter, is right, and really do it in an open-minded way. And of course what goes along with that is that observers who would like to test this way find it very hard to get observing time and so on. I mean, this relates to the whole issue of whether the complete lack of balance in the way the observational programs and the funding are conducted. There's no question about that. I don't think that anybody would argue about it.
I've always said that the cause of the troubles is the American graduate school. You get one person who then lectures to his students in graduate class, and because you have a system, you see, when we had graduated first degree, we were independent. We could thumb our noses at the professor, and in fact the best way to get ahead was to do something that the older people didn't agree with, and to be right. That was the way to do it. And but in the graduate school, you all have to learn what you're taught, what the professors are teaching you, and then those people go out and get jobs, and they have another graduate, their own graduate school, and it just tier after tier. You get a few places like Caltech or like Harvard, and they set the fashion for every place.
I think there's a problem with graduate education. I think graduate education is not teaching students to think, to be independent researchers. I think it's teaching them to be part of a scientific society. And too much, especially students that are at the so-called elite institutions, I think they're taught too much the paradigm of their advisor.
All of us, whether or not we served in uniform, are veterans of a war in which freedom and free government are at stake. Such fullness of knowledge is the direct function of education. Most of us work hard to provide our homes with every possible comfort for our children. We safeguard their health. We strive to set before them good examples of moral living, of manners and deportment. Possibly, we even pamper them. Yet complacently, even carelessly, we commit our children to schools of which we know but little. We cannot meet the complexities of modern life with outmoded school systems. We must keep our educational standards abreast of the swift-moving times in which we live, if we hope to preserve our national heritage and our American way of life, the American way.
When I was director of the National Observatory 20 years ago, there was a very well-known astronomer now. In fact, she's just won the Cosmology Prize. That's Vera Rubin. She was carrying out a program at Kitt Peak at the National Observatory of observing faint spiral galaxies with a view to looking to their redshift distribution, their velocity distribution. And this was a program that everybody thought was a good program. And so she'd been given observing time, and at the end of about a year, she had completed about a third of her program. And so she actually wrote a little paper pointing out that she was getting results very different from the ones that were expected. And we had our usual meeting. And when we got to her program, which was an ongoing program, so people just looked it over, the leading extragalactic astronomer on my committee of that day immediately said, well, look, she's getting this result. It doesn't fit. It has to be wrong. I recommend that we stop the program. That was his position. And what was interesting to me was I sat there and listened to this discussion. And the majority of the people, because of his level of knowledge and authority, went along with him. So the recommendation of the committee was that we stop the program. Well, I had the last word, so I ignored it. But most people don't. And the peer review system and NASA itself, which is very conformist, will always do just that. That's one of the reasons why the road ahead is hammered out. As Hoyle said, anytime you point a new telescope at the sky now, you're only going to find what you already know is up there.
I have a lot of trouble with the academic world, the same as I do with the Bible Belt. It's the same kind of trouble. It's the same kind of trouble. It's because they get a picture of this world which they are sure is right.
Yes, yes.
And they hang on to it for all they're worth. But you know, I often point out that I am probably more unorthodox than anyone who has ever burned at the stake. It's illegal now.
Illegal burning.
It's illegal now to burn somebody to the stake in your backyard.
Peculiar galaxy NGC 7603, discovered 30 years ago by Halton Arp, is one of the more striking examples of galaxy-quasar connections. It has recently been re-examined after the discovery of 2 new quasar-type objects embedded in the connecting filament. The renowned optical astronomer Margaret Burbidge has for decades been a central figure in the struggle to bring controversial observations such as NGC 7603 to the attention of conventional astronomers. And for her fairness and untiring efforts in the field, she has become one of the most widely respected women in astronomy.
There's a very interesting galaxy known as NGC 7603. It's a Seyfert galaxy. That means it has one of these active nuclei with strong emission lines and a lot of activity, obviously, going on in its center. And it was studied years ago by Chip Arp in his Atlas of Peculiar Galaxies. It has a spiral arm that seems to come right outside of the galaxy, trailing right out, and it ends up on a fainter galaxy, but it ends right up as though it's connected the nuclei of the two galaxies.
In the Atlas of Peculiar Galaxies, which was published in 1966, that was the point of the atlas, and one of the objects, just to illustrate what a peculiar galaxy is this what is now famous NGC 7603, and this is the central Cepher, which means just a very, very active galaxy with a lot of energy in the nucleus and a lot of explosive energy and so forth. And here is the high redshift companion here, and you see it's joined by a filament, a material. It turns out from the observations that this filament of material is material of the galaxy, gas and dust and stars and so forth. It's been drawn out in the ejection. But the astonishing thing and the controversial matter is that this galaxy is a much higher redshift than this.
Now, NGC 7603 has one redshift of about 8,000 kilometers a second, and the other galaxy has a much larger redshift. So how can they be connected? Well, these data were published years ago, and everybody said, well, this is just a chance location of a background galaxy near an interesting foreground galaxy, and that spiral arm has nothing to do with it. It's just the whole thing is just a chance.
If you see two objects close together with very different redshifts, you only have one of two explanations. One is, as I say, that a large part of the redshift has nothing to do with distance, and the other is that it's an accident. So the real issue that you come down to is how frequently do you expect to see accidents?
If you look carefully at the pictures that were taken of this field, you will notice two faint stellar objects that are in that spiral arm. One is close to NGC 7603, and the other one is close to the faint companion galaxy.
In the year 2001, when the two young Spanish astronomers worked on this with the Las Palmas telescope, they saw that there were these two condensations, stellar condensations. They looked like quasars, but everybody would have said that they had to have the same redshift as the central galaxy because they were obviously in this filament that had been ejected. What they found was that each of these objects had a much higher redshift, and that the filament itself had the same redshift and spectral composition as the galaxy from which it was ejected.
And they got some spectra using what's called the Nordic Optical Telescope in the Canary Islands on La Palma. It's not a very large telescope, but they got some excellent data, and they got spectra of these two faint objects, one by 7603 and one by the companion galaxy, and believe it or not, they showed that both of them were quasars. Not very high redshift quasars, but definite quasars.
Two of these quasars. Now this one will turn out to be quite good, but it's a very
It's a fairly big blow up. It's a couple of arcs that get across. But it looks like it's extended.
Anyway, it looks redshift.
So we'll go ahead and move it and then narrow it up.
The chance to have many quasars around a galaxy as a background objects. Of course, you have some chance, but these are very, very low, and this is what what should be answered. This is what should be answered. NGC 7603 is a very special case of this correlation. You find not only three objects with different redshifts in the neighborhood of a major safer galaxy. You also find the filament connecting all of them. So this is more important because the probability to have all these objects, not only in the neighborhood, but exactly in the filament is extremely low.
The galaxy, which is an active galaxy, two low redshift quasars, and another galaxy with twice the redshifts. In other words, you had four objects all connected together, apparently, by a luminosity, by a luminous bridge, each with a different redshift. Now that, I would say, is pretty conclusive evidence for the existence of non-cosmological redshifts.
We were lucky because we have found that the object has more controversy than expected. If in the past Chip Art thought, and Barbies and all other people that have dedicated some effort to research this object, if they thought that there were two objects connected by a filament with different redshift, now we have discovered that there are four objects all connected by the same filament and all of them with very different redshifts. So the Doppler redshift area is discovered.
I think they have to look at it, and I think it's one of the most striking results that we have available. How they can make sense of it other than saying that these objects, that these redshifts of connected objects that are the same, more or less the same distance from us, that these redshifts have non-cosmological components to them.
The topic of the anomalous redshift is very important for most of the areas related with cosmology and extragalactic astronomy nowadays. If we assume, as it is done nowadays, that all the redshifts are pointing the distance of the galaxy or the quasar or whatever, of course the results will be very different than assuming the other thing, that the redshifts are due to other reasons. The distance of the quasars and the galaxies will be different, the energies involved in the process will be very different, so a lot of astrophysical processes will have to change.
Conclusive evidence that the expanding universe was not correct, and that the redshift distance law was not correct, and that we had to have some way of creating new galaxies with high redshifts.
It is normally argued that the Big Bang, for instance, the Big Bang cosmology, is against the anomalous redshift question. And of course, the Big Bang theory is the most important theory that we have nowadays to explain all that we know about cosmology, which is not too much, in my opinion.
There's a large body of work going on, observational work, theoretical work, which is based on the assumption that quasars are at their cosmological distances. If it turns out seriously that we're right, then all that work is in vain. We don't know anything like as much as we think we do by saying that the quasars are far away. And that's another huge problem for people to face up to.
One of the frightening things, I think, for conventional astronomers is to accept the fact, or to realize that these intrinsic redshifts for the quasars and peculiar galaxies and so on, active galaxies, means that a lot of the things which we thought were out at great distance in the universe are very much closer in. And in fact, you would have to say that what we call the local supercluster is much more crowded and contains many more objects than we previously thought. And then the question comes up, well, what is out beyond the local supercluster, and can we with any certainty identify any objects that are out there?
Aware of what of our interpretations, because we cannot distinguish which objects have cosmological redshift and which objects have non-cosmological redshift, then we cannot trust the redshift indicator as a distance indicator.
People who work on the origin of the universe, they ought to look at data of this sort because they've got to understand this. And I've heard good friend astronomers say, well, there's more out there in the universe than we understand.
What's really happening in these systems is that the centers of the galaxies are the places where creation is taking place rather than just in a big bang. And so you're looking at all these mini bangs where matter and energy are actually literally being created. And this is an old idea which is not ours. Originally it was due to the very famous Armenian astronomer Victor Ambatsumyan, who only died a few years ago, who also argued that galaxies which appear to be coming apart and objects that are coming out of them are coming out of them. Very simple idea, but Ambatsumyan, who was a very well-known theorist, always said you must look at the observations, and maybe if things are coming apart, appear to be coming apart, maybe they are coming apart. Conventional astronomers don't allow things to come apart. They always say there's enough dark matter in the system to hold it together.
I've come to the conclusion that what it is that will unseat an established prejudice, a strongly established prejudice, is one observation. One single observation, usually a very simple one.
The conclusion was very, very strong just from looking at this picture, that these objects had been ejected from the central galaxy and that they were initially at high redshift and the redshift decayed as time went on. And therefore we were looking at a physics that was operating in the universe in which matter was born with low mass and with very high redshift, and as it matured and evolved into our present form, that we were seeing the birth and evolution of galaxies in the universe.
If protoquasars ejected from the nucleus of active galaxies themselves evolve into new, younger galaxies, astrophysicists must find experimentally and observationally the mechanisms which describe this phenomena. One model explains that the protoquasars are ejected, trapped in the galaxy's extreme magnetic field, aligned along the spiral arms, thus explaining the torn, disturbed features often observed in the galactic medium, and the frequent appearance of high redshift companion galaxies attached by filaments to a lower redshift parent galaxy. The other and most frequently observed alignment is when quasars appear to have been directly ejected out of the galaxy's active nucleus along its line of least resistance, creating a field of systematically high to low redshift quasars, or younger to older evolved protogalaxies. This is exemplified in innumerable systems like the one around the galaxy quasar field of NGC 3516. If one disregards the proposed redshift distance to these objects, observation clearly points to ejection as a likely explanation for their close vicinity to the central galaxies around which they are found. These results, though preliminary, are promising developments which may lead the way to new and exciting insights in cosmology.
One of the best and earliest of the really controversial things was a Seafoot galaxy known as NGC 4319, which Chip Arp discovered that it has a protrusion coming out in the south direction from it, one of its spiral arms, and ending up on another galaxy known as Markarian. And people have tried to explain it away in all kinds of ways and then tried to take false pictures to show that it's not there. But I've seen the good pictures, which were the first really good pictures were taken by Jack Sulentic.
NGC 4319 was part of some work that I did in the early 80s when I was a young astronomer, a young faculty member, and people were coming up to me and saying, oh, I've written a paper to show that what Chip Arp has done is wrong. There were at least 3 famous papers right around 79, 80, 81, and it took about 5 minutes to look at these papers to see that they they were flawed. And one of them was a paper that claimed to show no connection between NGC 4319 and the quasar Markarian 205. So at that time, I had the opportunity to work at JPL using the new image processing facilities that had been developed for the Voyager program, in fact. And it took 1 hour's effort to show that there was some kind of a luminous feature between those two objects. I don't know what it is, but there's no question that there is a luminous feature, and it cannot be dismissed in the ways that it was dismissed in the early 80s.
Suddenly there appeared press releases from Space Telescope Science Institute, which was the research arm of NASA's Hubble Space Telescope. And this press release said that they were not connected. And it gave a Hubble Space Telescope picture. It was not very deep, and you could just see two objects and no connection between them. And in this press release, then they said that this proved that there was no contradiction with the current expanding universe paradigm.
No connection between the two objects. So I looked at their picture, then I downloaded it, and it took me 5 minutes to show that it's still there. Now, I don't know what it is, but I think you face up to the existence of the feature, and then you consider conventional and unconventional explanations. But I was really surprised that they felt it necessary to issue a press release saying, it's not there, it's not real. Well, it's the same thing we saw 20 years ago.
But it's hard to get people to look at this because they don't understand it. You see, it's again the non-cosmological redshifts.
Realized that the people who had been processing the pictures and released it must have known that the bridge was there, and yet they chose to try to convince the public that in fact it wasn't there and that everything was right with the current expanding universe paradigm.
It's a strange attitude. I don't understand it as a scientist, really. I think that news release could have generated much more interest in astronomy than many of the more conventional news releases, because people would be talking amongst themselves, gee, what could that be? And then various people could offer scientific explanations. But to just sort of close the door, in a way, you could argue that Chip, or someone like Chip, who believes in an alternate interpretation, I'm sitting in the middle of the bridge, so it could be either way. He should feel strong, because I interpret that as a manifestation of fear and uncertainty. Because if I really had confidence in my paradigm, I'd put it right out there and say, well, yes, there is a bridge there, but it's either this explanation or it's that explanation, but certainly it's not what Shaparo says. But instead to just say it isn't there, that's a manifestation of fear, I think.
This misrepresentation of the results on a public level, published through a press release from a government-supported institution, which was not refereed and which gave the wrong information, seemed to escalate, in my opinion and my colleagues' opinion, escalate the controversy into a publicity campaign, which was sort of like doing scientific research by press releases in an attempt to defend, as a sort of a last resort, a dying paradigm in physics.
I don't know what more one can do than the data are there, they've been got, we have to make sense of it.
I think in one sense they think it's bad to, quote, confuse, unquote, the public. Because if you believe in the standard paradigm with all your heart, you know it can't be real. I know it can't be real. You know, if I try to be at all rational within the context of the current Big Bang ideology.
So if you have a cosmological theory that actually starts somewhere. I mean, I knew this when I was 10 years old, I think, sitting out in the backyard swinging with my brother, thinking about what would the edge of the universe look like if we got to the edge of the universe. And we, both of us, realized, even at that age, that the notion was somehow did not make sense. The universe can't have an edge, and it can't have a beginning, because if it had an edge, there has to be something on the other side, right? And if there had a beginning, there had to be something on the other side of that. And somehow cosmology, a satisfying philosophical cosmology to me, would have to start with that notion that it was always this way and it always will be this way. There's all kinds of things happening in there, but somehow the basic laws of nature are such that this exists.
Of course, this is astrophysics, this is science, and everything can be refuted. You have an explanation, you can produce an opposite explanation, so not everything is not so simple.
The theoreticians ought to be really looking at this theoretical problem, and the observers ought to be gathering much more data of the sort that we get. But I think they're all a little scared because it's an unpopular subject. They're worried about their jobs, and they're worried about getting moving on up the ladder. You know, if they're postdocs.
A young person in academia cannot afford to go against the Big Bang. He'd immediately lose his position, tenure.
Tenure, yeah.
As I said last night. And so there is this difficulty. You can't expect him to do that.
Don't collaborate with Chip Arp, or don't collaborate with Geoffrey, because if you do that, you will have problems to get a position in such a place. I received such a blackmail.
When I was a student, I was naive, and when I saw the chance to work with Chip Arp, he sent me a letter. This is 30 years ago, in fact. Good heavens, I hate to even think that it's 30 years ago. And warning me now that you may find some people put off by an association with me. And I didn't even understand what he was talking about. I thought, I'm just trying, we're just looking for the truth, aren't we? We're just investigating other areas, alternatives. But I found, indeed, that it was not this way, and that there was a great deal of hostility.
In my opinion, even if we are wrong, I'm not saying that we are right or anybody is right. From an observational point of view, we have a very peculiar object. So, and this peculiar object, it deserves some further research. This is what we need. And the interpretations are free and are to be discussed.
Now we're entering the realm of cosmology, and it is here that religion, philosophy, metaphysics, and science all meet. And make no mistake about it, they all play a role in our beliefs. The amount of data that we actually have to support any particular model is small. It's mostly consistency arguments. We can argue that the 3-degree microwave background radiation, yes, it can be explained within a Big Bang context, but I believe Fred Hoyle and Jan Narlikar and Jeff Burbidge have suggested an alternate explanation. And I'm sure we could find 10 more if the need were felt. But strangely enough, it's not. You don't get tenure in a university, you don't get promoted, you don't get recognition by looking too much into unpopular areas.
Cosmology is not a science. Has a lot of scientific aspects. We can know many things with the science. We can know how the galaxies are distributed, and these are measured with the observations. We can know how rich are how many metals are in the intergalactic medium or in some galaxy, and all these aspects are scientific. But with regard to some considerations about the beginning of the universe, this is in some way crossing the barrier of the science and going to something in between the science and metaphysical speculation, in my opinion.
Sociology is very important in science. People are in groups and gangs and cliques and clusters, and of course that enforces conformity. You want to be one of the boys, one of the, dare I say, one of the girls. It's the same after all. And so you tend to think alike. The longer you're together, the more you will think alike. I remember one famous group once, I asked them, how do you resolve disagreements amongst yourselves? And the reply was, we vote. And I thought, what a strange thing to do in science. Vote? I would think the best thing is that all 7 of you disagree. But there's a feeling that creates chaos. And the argument that we need some common thread or road to follow, for the majority to follow, in order to have some kind of organization to the whole scientific enterprise, there is an argument for that. But when it becomes all-encompassing, so that no other possibilities can even be explored, that is not good. And we're there.
Scientific notions take on, they have a lifetime of that really is involved in it gets involved with like somebody's job. It gets involved with, my theories are all in this particular, support this area. And so I don't want anybody in my department actually who doesn't work in that. I wouldn't want somebody in my department who is working in a very different side of things, like the steady state big banger kind of thing. If you are a steady state person, you're at this point you're feeling a little bit, paranoid anyhow, because most people said, hey, they found, Penzias and whoever he was, Arno Penzias, and the guy found there was the sky wasn't dark. There was a tiny little bit of light.
The cosmology as a science has begun 1 century ago with Einstein's theory. So in 100 years, you cannot produce a theory of everything. This is crazy. Even from a philosophical point of view, historical point of view, we have begun 100 years ago. In 1920, we thought that the Milky Way was all the universe. And now you want to produce the belief that in 80 years or something you have produced the theory of all the universe from the beginning to now. This is somewhat incredible, and not very objective.
The Big Bang is predicated on the assumption that from a point of view of physics there are no surprises in store for us, which is very unlikely.
When you start using words like infinity and perpetual and steady state and all those kind of things, you're really using a vocabulary that was formed here in a quite limited sort of part of the vastness of everything, right? I mean, we developed that vocabulary as a way of finding food, mates, building shelters, that sort of stuff. We didn't develop that vocabulary from vast knowledge or need to know about how the universe works.
We're at the level of where the observations are clear, in my view, but the theory is not. And one of the things that you find in science, and particularly in astronomy, is that people find it very hard to believe in observations if they don't got a theory, if they don't have a theory ready to explain it.
We also need theoreticians. Observations without any theory don't work. And theory without any observations certainly don't work. And the problem is to get them together. The problem is to get them together. We need some glue.
To anybody with an open mind, that should really prove the case that that quasars are associated with galaxies that must ordinary kind of redshifts, while the quasars have higher redshifts. Therefore, they must part of the redshift must be non-cosmological, not to do with the expansion of the universe.
Because I'm always thinking, if we can only be more rigorous, they will believe us. But I was wrong. I was very naive. It's got nothing to do with that.
The rolling of the Big Bang, it's largely been determined by the way people seized upon these ideas, and there's been tremendous amount of propaganda making claims that here we see everything happening and this has to be right.
The people that are in that field treat it like a religion.
And not very objective.
The reaction of the Orthodox astronomers to this idea is that it violates the Big Bang assumption, the Big Bang hypothesis, and therefore it cannot be true.
The amateurs tend to be more broad-minded than the people who have to earn their keep by being narrow-minded.
I got it.
Was this worked out by somebody, or was it, did it just happen by chance? Which is really the same thing as saying, did the universe happen by chance? And I have to say, when I look at it, it doesn't look to me at all like chance.